So last time we saw how to deal with general plane velocities. We saw that we can find the velocity of any point on a rigid body using the point where we know the velocity already. And basically what you can do is you can, if you know the velocity at one point, you can start to chain across different rigid bodies that are connected and figure out what everything is. We're going to go through and look at what general plane motion for acceleration looks like, and then we'll go through an example. We may not finish the example today, and in that case we'll finish it next week, and we'll show how you can also use one point that you know the acceleration of. You can use that to determine the acceleration at other points. So we're just going to consider a generic rigid body undergoing plane motion. In this case, we have 2 points, A and B. I've drawn their velocity and acceleration vectors. Generally, the velocity and acceleration vectors are not in the same direction, but I just drew one arrow for each of these. And then also we have both an angular velocity, omega, and an angular acceleration, alpha, as shown here. We previously said that we can express the velocity of point B, or VB, as being equal to VA plus the relative velocity B slash A. And then from that you can solve for V sub B slash A, which is equal to VB minus VA. Oh no, actually that's not what I want to write. Well, actually that is true, but it's also equal to omega crossed with R B slash A. And the omega cross R B slash A is what we found last time on Monday. So then we can show that the velocity of position B is equal to the velocity of point A plus omega crossed with R B slash A. Okay, so we're going to compute our acceleration by taking a derivative with respect to time of the velocity for position B. We're going to assume that we know the acceleration at point A in this case. And so we'll just take d over dt of VB. This will be equal to d over dt acting on VA plus d over dt acting over omega cross RB slash A. And we are going to need to use product rule for this second derivative term here, because the cross product is a multiplication when it comes to derivatives. Okay, so in this case, we'll find then that the acceleration at point B is equal to the acceleration of point A plus omega dot crossed with R B slash A plus omega crossed with R B slash A dot. And so we'll say that omega dot here is equal to our angular acceleration alpha, R B slash A dot. This is equal to V B slash A, which we just wrote up above as being omega cross with R B slash A. And then we can substitute these in, and we will find that a B acceleration at point B is equal to acceleration at point A plus alpha crossed with r b slash a plus omega crossed with the quantity omega crossed with r b slash a. And this is our acceleration. So when we're dealing with general, like 3D acceleration, you have to compute the cross product inside those parentheses first. When we have only plane motion, it's going to reduce down to something simpler, which we'll see in a moment. But the parentheses are actually important. You do need to do that cross product first before you do the cross product on the outside. So the order with cross products matters, is what I'm saying. So in general, omega crossed with omega then crossed with rb slash a not equal to omega crossed with the quantity omega crossed with rb slash a. And we can see that the first one is actually just 0 because you got a vector crossed with itself. Okay. So like I said, this is the acceleration in general. And then for plane motion, it's going to simplify. For plane motion, we're going to have that our angular acceleration is equal to some scalar alpha in the k direction. That alpha scalar can be a function of time, though. It doesn't have to be a constant. And then omega is equal to, again, some scalar value in the k direction. And then from here, if you go and plug those in, you'll find that the acceleration of point B is equal to the acceleration of point A plus this alpha k hat crossed with r b slash a minus omega squared times r b slash a. All right, any questions before we go on to an example? All right, in that case, we're going to go on to example 3 here. We're going to consider the following linkage system as shown here. We're asked to determine the angular acceleration of the link BC and the acceleration of point C at the instant shown. We're going to start off by choosing a coordinate system. In this case, we're going to use a Cartesian coordinate system. And I've put the origin at location A. Since we have multiple rigid bodies in this case, even though we're rotating about a single point, that first rigid body AB is rotating about a single point, the link BC is not going to rotate about that point, so you do not want to use polar coordinates in this case, which is why we're going to use Cartesian. From here, we're going to go to determine our absolute and relative position vectors. Since our origin is at point A, we're going to want to define everything we're going to want to define B relative to A, and then we're going to define C relative to B. It doesn't make sense, and it's not correct to define C relative to A because they are on different rigid bodies. They're not on the same rigid body. So we'll just start with RA, which is just our 0, 0 position. RB, as drawn here, this is going to be equal to A in the I direction. And then RC, as drawn, or as shown, is going to be at A plus B in the I direction plus or minus H in the J direction. Then RB slash A will be equal to AI. In fact, we'll carry that out. So this is going to be RB minus RA, which will then be AI minus 0I minus 0J equal to AI. And then we also need RC slash B, so C relative to B. And in this case, we're going to get RC minus RB equal to A plus B in the I direction minus H in the J direction minus AI, such that RC slash B is equal to BI minus HJ. Okay, from here we're going to go and determine our velocity vectors. We'll start with point A, and then we'll use point A to go and find what B is. And then we'll use point B to go and find point C. So first, VA equal to 0I plus 0J. Our VB is going to be equal to the velocity at point A plus omega 1 K crossed with R B slash A. We are given, although not explicitly, I didn't explicitly state this, but you're given omega 1 and alpha 1, meaning that they would be known quantities in this case, whereas omega 2 and alpha 2, the angular motion of the link BC would be unknown. So omega 1 is going to be equal to just a scalar omega 1 in the k hat direction. Alpha 1 will be some scalar alpha 1 in the k hat direction, because we're only dealing with plane motion right now. So then our velocity VB is going to be equal to 0I plus 0J plus omega 1 k hat crossed with RBA, which is just A in the I direction. And so then we'll find at the instant shown that the velocity at point B is equal to A times omega 1 in the J direction. With that being said, we're now going to solve for the velocity at point C. And so we'll write this out using B as our reference point. So velocity at point C will be equal to VB plus omega 2 k hat crossed with RB slash C. You can now write this out. We'll get A omega 1 J plus omega 2 k hat crossed with vector BI minus HJ. And at this point, this omega 2 is unknown. And so we're going to solve for both omega 2 and for this velocity vc. The way we're going to do that is that we know the velocity at point B. We're going to express the velocity at point B. Well, we did it already with respect to point A. We're going to express the velocity at B with respect to point C as well. So we can say that VB is equal to VC plus omega 2 k hat crossed with R B slash C. The next thing we're going to recognize is that due to the geometry of the problem, and I'll scrub just for a moment, point C can only move in the vertical direction. It's constrained to move in the vertical direction. So our VC must be equal to some scalar VC in the j hat direction. So from here we'll get that A omega 1 j must be equal to VC j plus omega 2 k hat crossed with minus bi plus hj, and this gives you bcj minus b omega 2j minus h omega 2I, or in other words, this A omega 1j must be equal to minus h omega 2I plus vc minus b omega 2. That is in the j hat direction.
Why are we adding the omega 2 k hat across RBC instead of subtracting it?
So you're saying, well, here we had a positive, and you're asking why are we subtracting?
Like it's saying BC is equal to VB plus omega 2 k hat crossed with RBC. And then
Oh, because it should actually be up here. This should be C slash B. So yeah, that's why. Yeah, it is. They are the negative of each other. You are correct. And so there was a mistake right here, and this should be R C slash B, not B slash C. From here, we're going to equate components. In the I direction, we're going to get minus h omega 2 equal to 0. And then from here, we're going to find that omega 2 is equal to 0. And then in the j hat direction, we're going to get a omega 1 equal to Vc minus b omega 2. And we just said that omega 2 is 0. So then we now know that the velocity vector at point C is equal to a omega 1 j hat, and the angular velocity vector omega 2 is equal to 0k, 0 in the k hat direction. All right, we're now ready to go and determine the acceleration vectors. Again, we're trying to find the acceleration, the angular acceleration of the link BC and the acceleration at point C. We're going to start with point A, which because it's pinned, it's going to have 0 acceleration in both directions. Then we can write point B as being the acceleration at A plus the relative acceleration of A, B slash A. This will be equal to A plus alpha 1 K hat crossed with R B slash A minus omega 1 squared times R B slash A. And we know that AA is 0, so we'll just eliminate that right now. And then from here, we're going to get that acceleration of point B is equal to alpha 1 K hat crossed with A in the I direction. And that's the only thing we have. Minus omega 1 squared A in the I direction. From here we can go and solve for AB, and this will be equal to minus A omega 1 squared I plus A alpha 1 in the J hat direction. Oops. I accidentally turned that off.